Oh, here we go.
Okay, can you see the proper screen here?
Yes.
All right. So as you heard, I'm Ken Farley. I'm not a teacher in a high school. I'm a professor at Caltech, and I'm also a project scientist for the Mars 2020 Perseverance rover mission. So I'm going to give you an update on what the rover has been doing and give you some background on why it's been doing it. And I'll start off by saying a little bit about what the project scientist role is. I've been working on this project since its inception in 2013, working as one of a very small number of scientists working with the engineers to design and build Perseverance. And the role of the scientist at that stage is just to make sure that the engineers understand what science needs. Once we got very far along in the project, and especially now that we're on Mars, I lead the science team. The science team is huge. There are close to 550 scientists on this mission. So it is an enormous team guiding this rover around. So we've now been on Mars for 553 sols or Martian days. So that's going on 19 months, something like that. So I want to tell you just a little bit about what this mission is about and what we've been doing. And I want to start with the one thing that if you know nothing else about Perseverance, the thing you probably know because it was covered in the newspaper, we successfully landed. And I want to just say a little bit about that. And I want to hopefully roll some video that is pretty spectacular. So I'm going to tell you about the landing site shortly, but this is it. This is an orbiter image from a previous Mars mission. And there are some features that I'm going to talk about in great detail, but the key points right now are that this is a crater that has a delta in it that was produced when a river flowed into a lake billions of years ago. And for scale, this little crater here is 1 kilometer across. So this was our target. We wish to arrive to study the delta, and I'll tell you about why that is in a minute. We had a kind of a landing capability that we thought it very likely we would land on this flat area right in front of the delta. Turns out that's not what happened. We landed over here, and I'll show you a little bit about why that happened. But first, let me put these names on here. So this is the delta, and you're going to see these cliffs in the video I'm going to play. These cliffs are about 40 meters high. You're going to see this crater, which is called Hahutsa, and you'll see this area, which is called Seta, which is, if you have a good resolution screen, you can see it's kind of corrugated, and it's filled with sand dunes. So you'll see those both in the video I'm going to play and also when I talk about the science that we've been doing. So what you're going to see here is in real time, it is something like the last 60 or so seconds of entry, descent, and landing. So by this time, the spacecraft comes in on a ballistic trajectory. It doesn't orbit at all. It is going straight in. And the first thing that it does is aero brake. Then it deploys a parachute, and you can see that in the little sketch down here. Here's the rover all squeezed up inside an aero shell, which can aero brake. Then we drop the heat shield, which is the piece of the aero shell in the front. We deploy the parachute. We come down on a parachute for a while. We cannot land on the parachute because the Martian atmosphere is so thin that if we only were on a parachute, game over when we hit the ground. So you got to do something else. And that's something else that Perseverance used, very similar to what the Curiosity rover did about a decade ago. We drop out of the back shell and the parachute and go into rocket-powered flight. So this video is going to pick up just when rocket-powered flight begins. But there's a new thing that's going on here, which is that during this rocket-powered flight, the spacecraft is taking pictures of the ground and is using some onboard logic completely autonomously to decide where the safest place to land is. And contrary to our expectation that it would land in this nice big flat area that's, it's like the size of 10 Disneyland parking lots, it didn't. So here's the delta. This is flipped a little bit. It's north is to the right. Sorry about that. But here we go. So the spacecraft is now figuring out where it's going to land. It decided it couldn't land over there. It cannot land in any of this area called Zeta. Can't land over in this area that is filled with boulders. And I'm going to show you some of the images of this area. And so I should have said, we started out at an altitude of about 2 kilometers. So we're dropping pretty fast. And now you're going to start to see the rockets interacting with the surface, blowing the dust away. And here's what's really cool. There are enough cameras on this during entry, descent, and landing that you can watch what happens. We literally winch the rover to the ground. As soon as the wheels touch down, we cut these cables and the rocket-powered descent stage flies away. So there it goes, flying away. And I hope all of that, I don't have the best bandwidth here, so I hope that worked. But at the end of the day, you wind up with the rover sitting completely by itself on the ground with nothing else around it. So we landed successfully, but we did not land in the place that we thought was most likely. Instead, we landed on what turns out to be a very narrow strip of relatively flat terrain. This is that area I called Zeta, filled with sand dunes, cannot land here. And this area is filled with boulders, cannot land there. So we land on something that is I'd liken to a sidewalk here. That's kind of a miraculous where it put us down. This is an image from the Mars Reconnaissance Orbiter. That is actually the rover. Here it is blown up, so you can actually see the rover. And this butterfly pattern is where those rocket engines blew the exhaust, blew the dust off of the surface of Mars. So we landed successfully. This was February 18th of last year. Very exciting to land successfully. I'll tell you, after investing 8 years of my life, we're helping build this thing. It was certainly very exciting. It was also very exciting because all of this was happening during the pandemic. Just getting the spacecraft to Florida for the launch during the early stages of the pandemic was an incredible challenge. We wound up having to do flights back and forth between JPL and Florida on a NASA jet because we couldn't use commercial aviation because it just wasn't possible. So we landed successfully, and I now want to tell you about what the purpose of the mission is and how we're going to go about doing it. I'm going to return to what we've actually done. So the Mars 2020 mission consists of all of the stuff that got us to Mars that I just showed you and the Perseverance rover. So here's the rover. It is about the size of a small car. It is very similar to the Curiosity rover. In fact, it was essentially a rebuild, except for all of the new stuff that we needed to accomplish our mission. In particular, I'll show you a lot of stuff about how we're collecting samples for potential return to Earth by future missions. So our central objective is to seek evidence of possible ancient Martian life. So this is a very specific statement, ancient Martian life. We are not looking for things that are presently alive today. And I'll explain to you why this is a very sensible thing to be doing, to be looking for ancient life, and now I mean billions of years ago, as opposed to looking for things that might be living in the soil or crawling around on the surface. So goal number one, seek evidence of ancient Martian life. And I'll explain why this is actually a very reasonable thing to be doing. Prepare samples for return to Earth. So this is the thing that will have, I think, really profound impact for decades to come, because we are going to collect the samples that a series of missions which are now in development will bring back to Earth in the 2030s. And these will be enormously sought after for analysis in terrestrial laboratories. And just to make a point that I hope is obvious, but if not, let me make it directly. The reason you bring samples back is there are many kinds of measurements that you can make on Earth that you could never make on a rover. And in my other life as a professor at Caltech, I have such a piece of hardware. I have a mass spectrometer in my lab, and it itself weighs more than the rover does. It's just such a massive piece of hardware, you can't fly it. And we also have an additional directive to do what NASA calls enable the future by testing new technologies. So I'm going to go through these one by one, give you some more of the details of what they really mean. Okay, so the first point to make is why we are looking for ancient life. And the reason is simple. The surface of Mars today is absolutely inhospitable everywhere that we have ever looked, and we have reason to believe. It is inhospitable to life as we know it. And that's because it is incredibly cold, it's incredibly dry, and one thing that it may not be obvious, it is also bathed in very intense radiation. And that radiation is both from the sun, especially solar ultraviolet, but also both solar and galactic cosmic rays. So this surface is not protected by an atmosphere, unlike here on Earth, nor is it protected by a magnetic field. So it is really, there's nowhere that anything we know about could live. But that's not the way it always was. And this image from the Curiosity rover, for any of you out there who are closet geologists, hopefully you will look at this and say, I think I recognize what those flat-lying rocks are. Those look like sedimentary rocks deposited in water. And that's exactly what they are. This is a lake deposit in the landing site where Curiosity went, called Gale Crater, from a period when Mars climate was really different, more than about 3.5 billion years ago. What we know then about the period 3.5 billion years ago when these rocks were being deposited is that it was warm enough for there to be liquid water. The atmosphere was dense enough to actually sustain liquid water. The water wasn't boiling away. And because there was an atmosphere, the surface was shielded from cosmic rays. And we also suspect that there was a magnetic field. So all of these things make the very distant past a much more sensible place to look for things that might have been alive on Mars at one point. So here's a kind of an artist conception, a picture of modern Mars, and an artist conception from what it might have looked like 3.6 billion years ago. We don't know exactly what that time period is. I would say it's uncertain to 500 million years. You know, being uncertain to 500 million years is pretty extraordinary. It's a large fraction of the entire geologic, all of geologic time, since the solar system formed 4.5 billion years ago. In any case, there may well have been a big northern ocean. There were definitely lakes. There were definitely rivers. That's the big discovery of the Mars exploration that has been done so far. It was once very different. Something happened about 3.5 billion years ago. We don't really know what it was. So I'll talk more about that as I go along. So why then do I say that it's pretty sensible to be looking for life in this time period on Mars? Well, the first is it appears that there were habitable conditions. There was liquid water. That's first and foremost, that is the thing that people believe is required for life, is that there be liquid water. Perhaps more subtle, but I think equally important, is if you look at exactly this age, about 3.6 billion years ago, this is when we have the first evidence of life on Earth. And that's shown in this image on the left. This is a kind of a rock called a stromatolite. It is produced when microbes growing in a shallow lake or sea form a mat that holds the sediment together. So the thing on the left is a fossil of microbial life from 3.5 billion years ago, 3.6 billion years ago. And the thing on the right is a modern example of the same thing. So we don't have to go very far to we don't have to go out on a limb to say we understand what the thing on the left is, because we can see things that are today living that look just like it. So the key point is, at the same time that Earth had life on it, and in fact, it looks like life was already thriving by 3.6 billion years ago, That is the same time that there were lakes and rivers on Mars. So why not? Why would you think that Mars wouldn't have life on it? So to me, that's a pretty compelling argument. And in fact, the place that Mars 2020 was directed to go by a big science community-wide set of workshops was to a place called Jezero Crater. And that's shown in this image here. What you're looking at is the rim of Jezero Crater. That's this here. It's about 1 kilometer high. The crater is about 40 kilometers in diameter. And you can see the river channel coming in. And then this feature, so this is not an artist's conception. This is a real set of images from an orbiter. This is a delta. We know exactly how this forms. The river is flowing along, has enough turbulence to suspend mud and sand. And as soon as you hit the slack water of the lake, that turbulence stops and the mud and sand settles out. So this is a very familiar phenomenon. And that allows us to actually draw or have an artist sketch the idea that this crater once had a lake, but we know more than that. We can tell because there's an inflow channel coming in here and an outflow channel there. So we know that this was what's called an open system lake. Water flowed in and water flowed out. And that allows you to say what the minimum depth was. So this was a lake that was 40 kilometers in diameter and hundreds of meters deep, at least 200 meters deep. That's a very large lake, even by terrestrial standards. We don't know how long it was there, but there was a big lake in this crater in the distant past. Okay, so that was why we went to this place, because a lake is a great place for things to live. And what's even better is to have a delta. And I just want to say a little bit about the delta, because you're going to see the geology that I'm going to show you from Jezero Crater is easily understood looking at this analog from Alaska. So of course, this is a delta. The river is flowing out into a bay. And a couple of features I want to point out here. Notice how the channels braid. So this is called a distributary network. It's a very typical way that that deltas work. We can see that on Mars. And then the other interesting thing about this is you see that it is covered with all these different colors. This just drives home the point that deltas are a really good place for things to live. So these are presumably some kind of algae or some kind of microbial life living in the mud. And then this living stuff is going to get buried. And in this relatively placid environment, it is well preserved. So not only is this a really great place to live, but it's a very good place for evidence of that life to be preserved into the geologic record. Compare that to your favorite, Sierra and Mountain River. You're not going to find any fossils in the boulders and sand that are coming off of some mountain in the Sierra. Instead, you go to a place where deposition is very placid and it doesn't destroy the evidence that life was in it. So this is what we think we have in Jezero Crater. So I'm gonna show you more of that in just a minute. I just want to show one thing about this directive to enable the future. So this is a little bit of a digression, but it fits within what we did in order. So we landed, and the first thing we did is we flew the Ingenuity helicopter. There are a lot of reasons for that I can talk about later, but it had to go right away. So this is a technology demonstration. So that is NASA speak for, they weren't really sure this was going to work, and it is not essential for the rest of the mission. It is simply to demonstrate a capability. And the challenge of flying this helicopter is that the Martian atmosphere is only 1% the density of Earth's atmosphere at sea level. So you cannot use your hobby shop drone on Mars. Instead, you must have very large blades. So this is Ingenuity. The blades it's a pair of counter-rotating blades on a single shaft. The blades have a diameter of over 1 meter. So this is a very large set of blades. And it worked remarkably. So let me just show this. So this is, let me go back to the beginning. This is just a test flight where it hovers, and you might be able to see the blades spinning. You will also see it occasionally rotate itself to demonstrate controlled flight. There it goes. So, and you see how stably it's hovering. It's only a few meters above the ground. That's all it's designed to do. So this was its first test flight. It worked perfectly. And in fact, it went through the series of 6 test flights, which were part of NASA's objectives to demonstrate that flight could occur. It passed all of those with flying colors. The final test flight was hundreds of meters long, zipping across the ground. It only flies for something like 60 seconds because that's all the energy that it has in its battery. But in 60 seconds, it can fly a couple hundred meters. So it is been remarkably successful. It was not expected to last more than those 6 flights, but it is still with us. And I think it just did it about its 30th flight. So it is now doing reconnaissance. It is flying out ahead of the rover, taking images for us, and also developing new kinds of capabilities that will be useful for future helicopter exploration on Mars. So this has been a remarkable success. Okay, back to the science. So here we are again at the Delta. We landed here at what's called Octavia E. Butler Landing. And I'm going to show you images from the places that are in boxes right near the landing site, and then 2 parts of the Delta. So this is obviously part of the Delta. You can see this just the cliffs at the front. This little thing here is just an erosional remnant. It used to be connected. So this would be like if you go out into the desert Southwest, you will see buttes and mesas. That's exactly how they form. They get eroded back from some original landform. So I'm going to show you this Kodiak Delta remnant because what we saw when we looked at these, very cool. So here's Kodiak. So this is about 700 meters across and about 40 meters high. And this is exactly what a delta should look like. What you're looking at in cross section is, well, so imagine you take this delta and you take a vertical slice into it and you lift it up and look at it on edge. This is what it looks like. The stuff at the top is easy to understand. The stuff, these flat lying layers at the top are nothing more than the sand and mud that's being deposited by these distributary channels. So that's why it's flat. What's less obvious when just thinking about it is, what are these sloping things? Well, imagine what happens when this sediment that's being carried by the rivers gets to the edge here. The water gets very deep very quickly, and the water and the sand and mud just plunge down that slope. So these are original depositional slopes. And the important thing that we learned from this delta is that when this was happening, the water level was right here, right where you see the transition from the slopey part to the flat lying part. So that's the equivalent of right here along the delta. So that's really interesting. The lake, when this feature was being deposited, the lake was only a few tens of meters deep. It was not at its deepest extent, which was, as I said, was hundreds of meters. So it was relatively shallow. So that's kind of interesting. But then we got a really big surprise when we looked at the delta front and we saw this. So what you're looking at here, again, think about the cross section of the delta. Take a slice into the delta and pick it up and look at it. What you see here in this lens-shaped feature is large boulders. So this boulder here, which is very rounded, is about 1 meter across. And there are many boulders, this is the biggest one, but there are many boulders that are tens of centimeters across, and they're all very rounded. Well, if you go back and you look at this picture, I hope your intuition would tell you, yeah, you're not going to move a boulder that's 1 meter in diameter in a flow that's as placid as this. If you want to move a boulder that's 1 meter in diameter, you have to have a big flood. So what we learned from this lens is that at some point, maybe you can imagine it happening here, is a massive flood came down the river and carved a channel. This lens-shaped feature is a channel in cross-section and deposited big boulders. And in fact, what we see on the top of the delta is lots and lots of such boulders. So it looks like the last thing that happened here, after there was a lake, a relatively stable lake, it looks like there were some massive floods, and they could have been much later. We don't actually know when they were present, but there's a history here that was a big surprise to us. And only now in the mission are we studying these rocks. So I'm gonna close with telling you what we've learned about these rocks, but I'm gonna go in order as we explored these rocks. Before I do that, I want to tell you what when we were exploring, what our key objective was. In addition to wanting to understand the geology of the crater and the history that is recorded in it, we are also collecting samples for potential return to Earth. So we have 43 tubes that are designed to take cores, and we seal them in these tubes. So the way this works, and I'm going to show you a video in a second here, is that this tube is mounted into the drill, and then we do rotary percussion drilling, and we take a core right into the tube, and then we take the tube into the belly of the rover and seal it. So we have 43 such tubes. So over the course of the mission, we will collect 43 samples. So these then will be brought back to Earth by a future mission, and I'll tell you how that's supposed to work at the end. So here's the video, and in the early days, before we were on Mars, I would show this video and just hope that this is how it would work. The reality is this is how it has worked. It's worked very well. So right now, the science team have been directing the rover to go out and acquire a sample. So the drill is mounted out here on the end of the robotic arm. There's also a whole bunch of science instruments out here that I'm going to show you some data from. We put 2 stabilizers onto the rock. And then if you look closely right here, oh, they blow it up. There is the rotary percussion. This is like a hammer drill that you get at Home Depot. Take the core. And now we're going to bring it into an incredibly sophisticated piece of robotic hardware. It's a remarkable piece of hardware to process this sample tube. So there it is being ingested into the rover through this very complex mechanism. And then here's the whole thing. Each one of these little holes is a place where a sample tube lives. So here's the filled sample tube. It is being manipulated through a series of stations where we take pictures, we determine how much sample is in the tube. So that's called measure the volume, and we seal the sample. So it is actually hermetically sealed. It's a gas tight seal. And then we take the tube and we put it back into its little silo. And I'll tell you ultimately what its fate is going to be. But for now, all of the samples we have collected live in this kind of beehive. And then the rover drives off to the next place. That's how it was supposed to work. And eventually that is how it did work. But we had some challenges, and I'll just mention in passing what those were. So here we are again at the landing site. Here's the area called Zeta. And then the area that I'm going to show you the most information from is this very cratered terrain here. So we drove on this path. The white dots are essentially where the rover spent each night. It's too cold at night to do anything but to try to stay alive. It gets down to about minus 170 degrees centigrade. So it's really, really cold at night. So we drove along here, and eventually we found a rock that we wished to sample. Well, our major goal as we were doing that is to try to understand what these rocks are. Are they deposits from on the bottom of the lake? That was what most of us thought. The delta is clearly a sedimentary rock. Maybe these are sedimentary rocks. Maybe they would be mud deposited out in the middle of the lake. But there's really not a lot to see here. And we were surprised that we didn't see any layering. So hopefully your geologic intuition would tell you sedimentary rocks are layered. Well, we didn't see any layering. Instead, what we saw is rocks that look like most of their features are controlled by eons of wind erosion. So these rocks are polished off right at ground level, not by coincidence. This is because the wind blows, picks up the sand, and the sand sandblasts these rocks. And you can actually see on all of these rocks what's called fluting. Fluting is the same, is also a process or a result of wind abrasion on rocks. So we really struggled to understand what these rocks were. In fact, we were on Mars for 6 months before anybody really started to offer up hypotheses for what they were, because they just didn't look like anything that we could distinguish. But the answer finally came when we started looking with our microscopic images. It took a while to get those microscopic images ready to go. And here's what we found. So here's one of those flat-lying rocks. And you can see it's covered with rubble, it's covered with sand, it's covered with dust. It's really hard to tell very much. So we have a tool that allows us to abrade a 4 centimeter diameter hole about 1 centimeter into the rock. That gets rid of all the junk that's on the top. This is a very powerful capability. And here's what we found on that first place we looked. There's a lot going on here. But to people that have looked at rocks, what you see is dark minerals and light minerals intergrown. If you've ever gone to the Sierra or to San Jacinto and looked at granite, this is what granite looks like. This looks like a coarsely crystalline igneous rock. And in fact, that's what it is. So this is a rock that was formed from a magma and crystallized relatively big crystals as it cooled slowly. So the basic lithology, the rock type on the crater floor, is igneous. But the other thing which you may intuit when you look at this is, oh boy, this looks really rusty. And it's got holes in it, and it's got cracks in it. Well, all of that is telling you this rock has interacted with water. And that's made the rusty, basically we've weathered minerals to release iron oxide. And these holes are indicating places where minerals have been wholesale removed. So this is a rock that has interacted with water, which is pretty cool. Well, we tried to collect this rock, and in that step where we retract the drill from the ground, all that happened is this rock was powdered, and the powder just fell out on the ground. So we did not get a sample. It was a grim moment on the mission. Everybody was afraid that we were not going to be able to collect any rocks on Mars, but we persevered, carried on, and we have now collected rocks successfully. Oh, before I get to that, we have some really fantastic capabilities for analyzing what these minerals are. So this is a microscopic image, but then we can place one of our instruments that does X-ray fluorescence mapping that tells us elemental composition at 100 micron resolution. So we make a map where the points are 100 microns apart. And here's what we get. So here's the image of the area that was explored with this tool. And you can see the color is indicating the relative abundances of iron, aluminum, and calcium. This is very powerful because this tells us what these minerals are. So for example, we can tell from the chemistry that the green material that's rich in aluminum is the mineral plagioclase. This is a very common mineral in igneous rocks. The purpley stuff is pyroxene, and the reddish stuff is iron oxide. So this is a really cool new capability for exploring rocks on Mars. But we were not able to collect this rock because it fell apart. Oh, sorry, even one more thing. We also could see in the microscopic images these white patches. And when we put the X-ray fluorescence instruments over these, we could see that they're salt minerals. So they are sulfate salts and also perchlorate salts. So that is a ClO4 anion salt. So this is indicating places where water evaporated and left salt behind. So this rock has seen lots of different kinds of interaction with water. We ultimately did successfully core a sample. So here's our coring bit showing off how it spins and percusses. And here's the first rock that we sampled. Here's the abrasion patch that I mentioned. And then we actually took 2 cores from this rock. And when we peered down into the sample tube, we could see right up where it should be a nice round core. So hopefully you all will resonate with the statement that this is about the size and shape of a piece of chalkboard chalk. I've discovered that if you talk to young people, they have no idea what you're talking about when you say that, but hopefully you all know how big that is. So there it is, nestled nicely in its tube, and the tube was sealed and stored on the rover. So big success there. It turns out, as we drove around on the crater floor and analyzed a bunch of different rocks, they're all igneous. Big surprise. There's no indication that the crater floor, the area out in front of the delta, has any sedimentary rocks. And I included this image from this rock that we called Sid. Again, for people that pick up rocks and look at them, which I certainly do, this is also a very familiar looking kind of igneous rock. So if you're wandering around out in the desert and you pick up a rock, you will see rocks that look like this, where you notice these white rice. They're about the size, shape, and color of little grains of rice. Absolutely characteristic of the mineral plagioclase, which I mentioned before. And even this shape here that's kind of shaped like a tooth. This is like you take your first year geology students out in the field and you pick up rocks and teach them, yes, that white mineral is plagioclase in an igneous rock. So that's the big surprise that they're igneous, because we know that there was a lake there, and in a lake there would be sediment deposition. That sediment must have eroded away, must have gotten blown away out of the crater, which is pretty interesting. And these rocks are not only igneous, but they've interacted with groundwater. And I am emphasizing that because we cored these rocks and stored them on the rover to be studied when we bring them back to Earth. And that's really interesting to have an igneous rock. It's important for many reasons, but one of the key reasons is these white crystals, for example, can be dated using radioactive decay methods with very, very high precision and accuracy. So I kind of threw around the idea that this crater had a lake in it, 3.6 billion plus or minus half a billion. I would be very surprised if, when these rocks are dated using radioactive decay means, that the ages are uncertain to more than a couple of million years at 3.621 billion years. So there's incredible what you can do in a terrestrial laboratory. So that's what the igneous rocks are good for. These rocks have interacted with groundwater, and so they're going to tell us a story about the history of groundwater on Mars. And groundwater is a potentially habitable environment. So maybe there's indications of life that might have been living in the subsurface, trapped in these alteration minerals that indicate interaction with water. So really cool sample suite that we got on the crater floor. So that was this area down here, and we mapped out two different kinds of igneous rocks. I won't go into the details of them, but one was this area called Sita, and the other is an area called Maz. So that was exploring around here. Then once we finished this, we decided to go on a very fast drive. So we left this area here and drove 5 kilometers to about here in 30 days. That is, previous rover missions have taken a year to go that distance. So we were in absolute pedal to the metal, because we had the capability to use autonomous navigation. So the rover takes pictures and decides where it is safe to drive and drives itself. So we essentially drove all day long. When it was warm enough and we had warm enough and enough energy, we just drove to get over to the delta. And so I'll just close by showing you what we've learned at the delta. So here's that area called Seta. Came up to here, and we've kind of wandered back and forth. These are, again, the cliffs of the delta, 40 meters high. And we drove up onto the edge of the delta in 2 places, this area called Enchanted Lake, which is where the rover is right now, after having gone all the way over here to this area called Hogwalla Flats. We wound up driving back. But I'm going to show you what we learned at this place called Hogwalla Flats. And before I leave this image, over the course of the next 4 months, this mission will be in the news, because we are going to be putting our sample tubes down on the ground in this area here called Three Forks. And I'll tell you why we are putting them down on the ground. This is going to be a big deal because this is going to be the thing that motivates the future missions. It's the target for the future missions to pick up those samples. So I'll tell you about that, but I want to show you where Three Forks is. It's this big flat area. Is incredibly flat. It's great for doing this transfer to the future missions. So let me show you what we found here at this place, Hogwallow Flats. Well, here it is. This whitish band that you see here, that's this. So here we are at this whitish band, and this hill behind it. Well, let me skip ahead. Let me show you what the hill behind it looks like. So here we have very layered rock. And we can see even in these images, when you zoom in, these are sandstones. Absolutely, these are water deposited sandstones, exactly what you'd expect on the Delta. What intrigues us is this area here, because this is much finer grained. This is mudstone, so it's much finer grain size. So we sampled two different rocks here, one of this kind of coarse unit up here at a place we called Skinner Ridge. And then we had a hell of a time finding a place where we could put the drill down without breaking these rocks. These are like dinner plates scattered all over the ground. And whenever we put the drill on them, we break them. So we finally found a fairly resistant one at this place, Wildcat Ridge. So here's what we see inside these rocks. So this is, again, the robotic arm doing its thing. Here's an abrasion patch in that Skinner Ridge rock. So here are the abrasion patches of these rocks, very different from each other. This, I hope you can all see, it is filled with grains, but those grains look a lot different than the grains in the igneous rock because you can see that they look like little rounded grains separated from each other by cement. That's in fact what they are. In fact, if you look closely at these with the microscopic capabilities we have, some of these are individual minerals. Some of them are little tiny rock fragments. So this rock is then a sand that was deposited by a river into the crater and then cemented together. And what we've discovered is cemented by carbonate, which is really interesting because carbonate is very useful for learning about, for example, paleotemperature, the temperature at which this rock was solidified when there was water around it. So that's pretty cool. We cored this sample, and the information it contains, just one point I want to make about it is, every one of these grains was transported by a river from somewhere in the headwaters of that canyon that I showed you. That headwaters is at least 40 kilometers wide. Places the rover can never go. We're not going to drive 40 kilometers up the river channel. So every one of these grains came from somewhere up there. And when they get studied on Earth, they're going to be a very rich source of information on places the rover cannot visit. So that's why we're excited about this rock. This rock, the one from the dinner plate terrain, you can't see very much. In fact, the little color variations you see are not grains because it's so fine grained. But the big surprise here is this is a mixture of mud and salt, sulfate salt. So what we think this rock is a time period when the lake was desiccating, precipitating salt, and also having mud settle out of suspension. This is a really interesting rock because this is amongst the most habitable places we know of on Earth. Places where you have salt flats. If you go to anywhere along the coast where there's a lagoon where you're precipitating salts, you'll see all sorts of things living in the muck, in the salty muck. Or even if you go out to Death Valley in the Badwater, you see the same sort of thing. Lots of things live in such an environment. So really interesting pair of samples that are very different from the igneous rocks. They're a very nice complement to the igneous rocks. So we're learning a lot about the Delta. I'm not going to tell you a lot of the details here, but we are having a press briefing on these very rocks a week from yesterday. So I'm not, the rules that NASA uses, I'm not allowed to tell you the details, but we're having a press briefing, so it's pretty interesting. We have not, I will just say, we have not discovered evidence of life. But we have found some really interesting things in these rocks that suggest we might be on the right track. So that's very cool. And here are the cores inside the drill bit. Here's the coarse grain sandstone. You can see all the grains in it. And here's the mudstone. Really successful acquisition of these samples. And then here's the final slide. We are not tasked, we, Mars 2020, are not tasked with bringing these samples back to Earth. And people always want to know why. Like, why can't we do that with this mission? Why do we have to wait for a future mission to do it? And the answer has two pieces. The first is what we are doing, driving the rover around and collecting those tubes, is already so complicated that just to build that rover used pretty much all of the capacity that NASA and JPL have to do such a thing. If we also had to invent the rocket and all of the other stuff you need to bring the samples back, which I'll describe here, there's just not enough people to do it. So it's very sensible to phase these things. So do the first thing first, and then do the second thing, and then do the third thing, spread out over multiple years. The other reason, which is very practical, is this also spreads out the cost. So each one of these missions is a multi-billion-dollar flagship class mission. And if you try to do it all at once, the budget isn't big enough. So again, you stagger it. So the plan is that Mars 2020, this is actually a plan that goes back a long time, but it is now being implemented. Mars 2020 collects the samples, and by a mechanism, which I will describe in a moment, transfers them to a lander with a rocket. And the samples are actually nestled in a sphere about the size of a basketball in the nose cone of the rocket. So we launch the rocket that contains this basketball called the orbiting sample. So 30 of the 42 sample tubes, 43 sample tubes that we have, we will make a down select. We won't bring them all back. 30 of them will be launched into orbit as this basketball. And then a third mission comes along and captures the orbiting basketball full of samples and brings it back to Earth. All of this is currently in development. So we're operating. These two missions are in development jointly by NASA and the European Space Agency. ESA is building this called the Earth Return Orbiter. And JPL plays a lead role in building what's called the Sample Return Lander, and other NASA centers are building the rocket. So the last thing I will say is that the way that we are going to transfer these tubes has to this follow-on mission been very interesting, because one of the things that is, I don't know that it's ever been done in planetary exploration, is to have multiple missions interacting with each other. But the decision has been made that Mars 2020 is very likely to still be operational when this lander lands. This lander will not land until 2031. So this rover needs to last another 8 years to literally hand off the samples to the lander. But I also told you that we were going to put down samples at Three Forks. So we're putting down some of the sample tubes at Three Forks as an insurance policy. In case Mars 2020 dies with the precious cargo inside, we will have put the samples down and made them available as a backup plan to be returned to Earth. So it's a very complex piece of choreography, how all of that's going to work. But if all goes according to plan, these samples will return to Earth in 2033, which is 10 years away. And many, many years ago, I was a graduate student, and I was hearing that samples are going to come back from Mars in 10 years. That was 30 years ago. So it's still 10 years away, but the process is well engaged. So I think we will see some very interesting continued discoveries by Perseverance exploring the surface of Mars, and then especially when these samples come back. So I'll stop there, and if there's time, I'm happy to answer questions.
Yeah, I was wondering, what do you use to clean
the drill bit between sample collections?
You're worried about cross contamination of one sample to another.
Yeah.
So there will be some dust transfer, and there's no way to prevent that. But as it turns out, most of what we are getting is actually core. It's not dust. And
Yeah.
so anything that's a rock, when it comes back, we'll know that's associated with a particular sample. The much bigger challenge, and this is just a generic kind of statement to make, one of the most important things that we could be looking for as evidence of possible ancient life is organic matter. And the problem with, or the challenge with this is that the Earth, when we built the rover, the Earth is just dripping with organic matter. And keeping the sample tubes and the drill clean enough that if we brought organic matter back, that we could say it came from Mars, that was a huge challenge. But yeah, so we don't worry so much about cross-contamination, but we definitely worry about Earth-sourced contamination.
Another question I have is, with the Mars dust, how does it affect the moving joints and everything in the rover?
Yeah, so this is a big challenge. The complexity of operating a rover on Mars may not be obvious. This is one of them, that anything that moves is going to get dust in it. So most of the joints are sealed. This is especially problematic in the drill, because not only is there dust blowing around in the atmosphere, but there's a cloud of dust as we hammer drill into the rock. There's a cloud of dust coming off of it. And most of the joints of the rover are sealed against dust intrusion. And that happens in most places within the drill bit as well, or within the drill as well. But there are other places it just has to be designed to be tolerant of getting stuff in it. And we have actually had what NASA speak as an anomaly when we actually had a rock fragment stuck in a mechanism where it should not be. And we spent about 3 weeks over Christmas of last year trying to get the rock fragments out of there. So that's one big challenge, is just interacting with the surface that's so dirty and dusty. And the other is the enormous temperature swings from day to night is really, really hard on things like electronics. And so many of the pieces of hardware have to be heated all of the time. And ultimately, this is the way that many components will ultimately fail, is from the big thermal swings that they see.
What charges do you have a lot of solar panels that charge batteries?
Yeah, no. So hopefully you can see my mouse. This black thing back here is it is the power source. It is a block of about 6 kilograms of a radioactive isotope of plutonium. And just based on the temperature difference, that plutonium is something like 600 or 700 degrees centigrade. And based on the temperature contrast between inside this black thing and outside, you can generate electricity. So it's not a nuclear reactor, but it is just acquiring that heat and turning it into electricity and pumping it into batteries. So we get, I forget what the exact number is, but we get something like a kilowatt hour per day out of the thing, which is great, and it will last a long time. So this mission is not limited by the thing that solar powered missions always worry about, which is the accumulation of dust on the solar panels, or dust season when the sun is just too faint to charge the batteries. We can work right through that. And we did. We've already gone through one dust season with no ill effect.
So it's like a Stirling engine that runs
Well,
on temperature.
it's a thermocouple, if that is familiar to anybody.
How many samples have you gathered so far of the 43?
We have collected so far 15 sample tubes. And one of the things we've been doing is when we sample a rock, I showed you that one rock that had 2 holes in it and said we collected 2 tubes. That's so that we can put one down in the emergency backup plan cache at Three Forks and carry another one with us. And so at this point, we have sampled 5 different rocks and into 2 different tubes each. So that's 10 tubes. And then we've also collected some blanks so that we can determine whether there's any, for example, organic contamination coming from anywhere. And we've also collected an atmospheric sample.
And what's the logic of burying this insurance population that it doesn't blow away or become lost, so that if it's necessary, that you'll know exactly where it is?
Yeah, so this is a good point. I should have said something about. What you see in the movies is seriously overblown. There is definitely wind on Mars. It's actually pretty strong wind in terms of velocity, but the atmospheric pressure is only 1% of Earth, so you would hardly even notice it if it was blowing past you. So it's not like there would be a giant raging dust storm and we would bury the tubes. We will know where the tubes are to within 1 centimeter relative to objects that we can be absolutely certain will always be there, like rocks sticking up out of the ground. So we'll know exactly where they are. And we are selecting places where no sand will accumulate. There are definitely places where sand dunes migrate across the landscape. We will not put it there. So there's not much risk that these tubes will be lost. And when we were originally designing this whole plan, NASA told us to design it in such a way that the tubes could sit on Mars for as much as 50 years, because they weren't sure, and still are not sure, when these follow-on missions will actually get there. And they don't. So you don't want to lose the investment in having collected them by either having them get lost somehow, or have the seals, that I told you they're hermetically sealed. You don't want them to, break open from thermal cycles. And so we'll know exactly where they are. I don't expect that'll be much of a challenge.
Thank you.
What's the power source of Ingenuity?
Say again?
What's the power source for the Ingenuity, the helicopter?
Yeah, so let's see if I can scroll back there. It is solar, and it's kind of interesting. It's a little bit too small to see, but maybe you can see a little plate right at the top of the blades. That's a little tiny solar panel. So the solar panel is mounted on the same shaft as the blades, and this is actually one of the challenges for this technology, because it's very hard to make the solar panels much bigger. So after Ingenuity does one of its flights, it typically has to rest a few days, charging up the batteries. And also, one unfortunate aspect of it is, as I mentioned, it gets really cold at night, and electronics doesn't like to get cold. So it does acquire more energy every day, but it's got to get through the night. So it has to blow a fair bit of energy just to survive the night.
Have you found any rocks that you do not have an analog on Earth? So anything different? This is only on Mars.
No, and in fact, one of the really interesting things that I think the last decade has shown is that essentially all of the things that we have learned over hundreds of years interpreting the geology and geochemistry and mineralogy of Earth is pretty applicable on Mars. We haven't really seen anything that the details are different. For example, the way sediment gets carried in water, because the gravity is only 40% of Earth's gravity, it's different, but the rocks look basically the same. And what this means is that the people that operate, on the science team of a rover, many of them are actually Earth scientists. They are trained as Earth scientists. That's my case as well. And so we can just look at these rocks. Like I said, when I saw that first rock that looked kind of like a granite, that was my first thought. Looks like a granite, and that's obviously a terrestrial bias. But so we have not found anything too surprising yet. Oh, that isn't really true. The one thing that we have not seen, but we have not been looking, but Curiosity has definitely seen. There are meteorites scattered around all over the surface here. So, for example, Curiosity has seen multiple iron meteorites. You would never see that on Earth because they disappear, they rust and get buried. The reason you can see them on Mars is just sitting there not doing anything for billions of years. So any meteorites that fall just sit on the surface.
You know, if there's any follow-on versions of the helicopter that might be used either on Mars or maybe Titan?
Yes, both. So there is a mission to fly a helicopter on Titan. I don't really know much about it. But one of the things I didn't say that NASA just recently announced is that cache that I told you we would put down in Three Forks. So the cache just means a collection of sample tubes put down for a future mission. If Perseverance dies, that is the set of samples that the future missions which are now being built will target. Well, without Perseverance, you may ask, how will they ever get to the rocket? Well, JPL is building a pair of Ingenuity class helicopters with a little claw underneath that will fly over to the cache, pick up the sample tubes and carry them over to the rocket. That's a very bold, very big step from a technology demonstration to basically a heavy lift, a heavy lift helicopter. But that's the plan.
Yeah, that's very interesting. It just like you said, that'd be a heavy operation, I would think, on a planet that has an atmosphere of so thin.
Yep. And the other thing is you don't have a whole lot of time, for example, to hover properly over the tube and gently lower yourself down and grab the thing. So there has to be some very quick and capable autonomy to get to the sample and get going, because you've only got a small amount of time when you can be spinning the blades before you run out of energy.
So would the helicopter be delivered to Mars on the next phase of this project, where you have a vehicle that comes down and lands to pick up the samples?
Yeah, and this turns out to be the original idea for how you would go about picking up this cache, is that the follow-on missions would bring their own little rover. And that became very complicated. And in fact, they came to the conclusion that the rocket and that little, what we call the fetch rover, would need to use a separate rocket to get to Mars. So now you got to buy two rockets, and rockets are very expensive. And when people realized, hey, we could use the helicopters to do this, they realized there was enough space in the back shell of the spacecraft that will land the rocket that will bring the samples back to Earth. There's enough space in there to fit two helicopters. And so the plan is that I believe that during entry, descent, and landing, there will be a step when the helicopters are simply released and they will fly themselves to the ground.
Well,
I look forward to seeing the video of that. And interestingly, Perseverance already has instructions, if it is still operational, to run the video and record all of this when it's going on, which will be it'll be an extravaganza when that happens in 2031. It'll make the news.
Yeah, I'm sure of that. Yeah, fantastic.
Okay, any other questions?
I have one question about the wheels. I remember they were having trouble with the wheels on
On Curiosity. Yeah.
on Curiosity. And so did they what kind of upgrade did they do for this one? Do you know?
Yes. So Curiosity rover, within maybe about a year started getting holes in the metal covering of the wheels. That metal was about the thickness of a soda can. And there were a lot of reasons why it needed to be so thin. It had to do with minimizing mass and minimizing the moment of inertia of the descending spacecraft. Obviously, they shaved it too far. And so for Perseverance, the wheels were completely redesigned. And the thickness of the metal covering the wheels, they are much thicker, and were tested in the Mars yard at JPL. So the Curiosity wheels, indeed, when we drove them around and around in the Mars yard, pretty quickly they got holes in them. The new wheels that we put on Perseverance went around, I don't know how many times, but no damage whatsoever. So I think that problem has been licked.
I have a question. Do you know what programming languages that they're primarily using to do the programming for these?
I don't.
Hmm.
Sorry.
Well, I want to thank you. That was extremely interesting. And I'm going to have to go. You have some websites for us?
Yeah, so just Google JPL Mars 2020 and you will find all sorts of stuff. One of the interesting things that we do is the minute the images arrive on Earth, they go up on a public website. So they arrive on a public website at the same moment they arrive for us. And this is always a kind of a hair-raising thing when we have a problem. So the world knows there are people who know how to look at those images and will immediately be able to tell. So for example, we kind of got stuck in the sand. It wasn't a big deal. A couple of days ago, we kind of got stuck in the sand. And there were people that were saying, oh my God, Perseverance is stuck in the sand just by looking at the pictures. So yeah, it's easy to find just go to the JPL Mars 2020 site.
Okay, thank you.
Thank you. It was great. Appreciate
Yes.
it.